Okay, my name is Victor Jimenez, and today I'm here to talk to you about a joint work with Manuel de Leon and Marcelo Epstein. Before starting, I would like to fix my main target in this talk. This goal is just to give you an overview about the use of groupoid distributions and foliations in material evolution. So my intention is not to give you a lot of technical details and proof during about 25 minutes. What I want is to convince you about the usefulness of this approach in the understanding of the evolution of materials. So let me start giving you a very brief scan of the approach. So the physical framework is the constitutive theory of materials, which was first started by Walter Knoll in his thesis, and it has been worked by a lot of authors like Truesdell, Wong, or Masden. So maybe the cornerstone of this approach is the discovering of a groupoid which codifies all the intrinsic properties of the material, and this groupoid is called the material groupoid. What happened with this groupoid is that this groupoid is not a Lie groupoid in general. So to solve this problem, we have constructed the so-called material distribution. And again, this distribution is well-defined, unique, and it is canonical for any simple material. And in addition, it is differentiable. Another important point of this distribution, it is that this distribution is also integrable. So we have the associated foliation, which is called the material foliation. And finally, by using the imposition of construction of this distribution, we obtain the so-called evolution equation. So here we have the key points of this approach, which are the material groupoid, then the construction of the material distribution, and the associated material foliations and evolution equation. So let me give you an index of this talk. We will start talking about the constitutive theory of materials, focusing on evolution material and defining only two properties, remodeling and aging. Notice that here we will only give some necessary ingredients to understand what follows. So next we will introduce the material groupoid, and finally we will talk about the material distributions and its associated material foliations and the evolution equation. So let me start. First, for us, a body will be a three-dimensional manifold B, and then a body time manifold will be defined as R times B, where R defines the time variable. We will think about this body time manifold as a projection on the time variable. So it will be thought as a fiber bundle whose fiber is the body. Then if we fix a time, we obtain what is called the state t at this time of the body. So a configuration is just a way of embedding the body into the real space, which for us is this R3. So a configuration will be an embedding from B to R3. Then a history of the body will be a fiber bundle embedding over the identity from the body time manifold to R times R3. And this guy will be presented as a fiber bundle, which is the projection on the first component. So, in other words, a history of a body is simply a differentiable curve of configurations. It's in such a way that for any time we have a possibly different configuration. So, in some sense, this history measures how the body is changing in time. Okay, usually we define a fixed configuration as the reference configuration. So up to now, we haven't talked about the intrinsic properties of the material. So to characterize these properties, there exists the so-called mechanical response. So roughly speaking, in a given reference configuration, the constitutive response at one point and at one time will be characterized by one or more functions depending on the associative matrix to the first derivative of the configurations at this time and at this point. So, in other words, our mechanical response, which is called the evolution mechanical response, will be a differentiable map from this domain to V. And V for us will be an arbitrary vector space. We will not be worried about the shape of this V, but in general this V will be the space of a stress tensor. So here the important step is that the evolution mechanical response can be redefined as a map over the space of these tripods, where here we have two time variables and then we have a one jet, or the first derivative of a local diffeomorphism from B to B, such that the image of X is Y. So let me take the vertical subbundle of C, B, then the fibers of V at a given point will have this shape, and we can also consider the space of all linear isomorphism between these fibers. This space is denoted by this, and what happens is that this space is in fact a Lie groupoid, and the element of this Lie groupoid, the morphism, are characterized by these triples. So what we are doing here is just to redefine the evolution mechanical response over a Lie groupoid, which is this groupoid, which is called the frame groupoid of this space. So here it starts the word groupoid by first time in our framework. Okay, we have presented the mechanical response. Let us explain a little bit why this map codifies the intrinsic properties of the material. Let us take 2 points, X and Y, and 2 at 2 instants, T and S respectively. Then what happens is that by using the mechanical response, we can compare these 2 points at these two different instances. In particular, what we have is that we can say that they are made of the same material if the constitutive properties are exactly the same, which is obvious, right? So in other words, we may say that they are of the same material if the mechanical responses are exactly equal, respect maybe different reference configurations. So here, there is an important result which says that this claim is equivalent to this one. So we may say that these 2 points at these 2 different instants are made of the same material if there exists a local diffeomorphism from X to Y such that it is a symmetry by the right of the mechanical response, or what is the same, it satisfies this equality for any other triple. So the existence of this kind of these kinds of triples permit us to say that two material points are made of same materials. Well, these triples are will be called material isomorphism. This notion is an important part of our approach. So let me show you just a simple picture in which we can say how the body is changing, and in the first step from T to S, the mechanical properties hasn't changed, so these material isomorphics exist, but in the next step at time R, all the mechanical properties has changed, so this guy cannot exist. Obviously, the mechanical response works to compare two different points at the same instant of time, in such a way that, for example, in this case, we cannot find any material isomorphism joining these 2 points at the instant S. So okay, let me just give you the definition of these of the properties. First, a particle is presenting a remodeling when all the points are connected by where the points at this space are connected by a material isomorphism. In other words, a material particle is presenting a remodeling when the intrinsic properties haven't changed in time. So the point is evolving, but the intrinsic properties are not changing in time. So all the points are connected by a material isomorphism. And we will say that the whole body is presenting a remodeling when all the material points are presenting a remodeling, or equivalently, the intrinsic properties of the whole body haven't changed in time. So, by definition, fix a particle presenting a remodeling and fix a time t0. Then, we can find a map from R to the frame groupoid such that for each t, the image is a material isomorphism joining these two pairs. So, by definition, we can guarantee the existence of this material isomorphism, so we are choosing just one for each t, so it is not so difficult. But the problem here is that the existence of this map doesn't guarantee the differentiability of these maps. So we need a more restricted definition. And then we arrive to the definition of a smooth remodeling. In this case, roughly speaking, a material point is said to be presenting a smooth remodeling is if we can ensure the existence of these maps, and we are not imposing that this map are global in the whole R, but this map may be defined in local intervals, but the only imposition is that the intervals cover the whole R. So this is a smooth remodeling and it is very intuitive, right? Then, on the other hand, we have the notion of aging, which is opposite to the notion of remodeling. In fact, a material particle is presenting an aging if it is not presenting a remodeling. So, in other words, a material particle is presenting an aging if the properties are changing in time, and the whole body is presenting an aging when the material properties of the body are changing in time. So if there exists at least one particle which is presenting an aging. So okay, we have remodeling, we have a smooth remodeling, and we have aging. So what about a smooth aging? Well, the smooth remodeling was defined using these maps, but aging by definition is the lag of these maps. So we cannot impose any condition of differentiability over any kind of maps, so it is not so easy to define a notion like a smooth aging, right? A smooth evolution in general. One of the problems solved by the material groupoid is to give a very natural and logical definition for any smooth evolution in the general case. So let me start with the material groupoid. So fix 2 points, then we will call xy material groupoid to this guy, which is the set of all material isomorphism joining x with y. What happened with this is that if x is different to y, this is not a real groupoid. So to obtain a real groupoid, we need to impose that x is equal to y, and then we obtain the x material groupoids. So notice that these points are fixed, so we are varying the time variable. So this groupoid measures the variation of the particle in time. So okay, this guy is a groupoid with a composition of one jet, so it is a subgroupoid of the frame groupoid, but it can be also seen as a subgroupoid of this groupoid, where here we have 2 time variables, and here we have the set of all one jets of local diffeomorphisms from B to B, such that the image of x is x. So roughly speaking, we are in fact just taking these triples with y equal to x. And this guy is again a Lie groupoid, so there is no problem. So okay, let me give you some results by using this material groupoid. The first one is the result characterizing the remodeling. What happened is that we can easily prove that a particle is presenting a remodeling if and only if the material groupoid is transitive. So transitivity is equivalent to remodeling in the case of the material groupoid. Another result, which is not so easy to prove, it is much more technical, is the following. A smooth remodeling is characterized by the condition of being a transitive Lie subgroupoid. So in this case, we can see how the word transitive is characterizing the word of remodeling, and the word Lie is characterizing the condition of smoothness. So we have 2 characterizations, for one for remodeling and another for a smooth remodeling. Then another one, which is also easy to prove, is that a particle is presenting an aging when the material groupoid is not transitive, right? It is really obvious, because a remodeling it is when this groupoid is transitive, then an aging should be when this groupoid is not transitive. So okay, transitive, remodeling, and Lie smoothness. So how could we define the smooth aging? So as you can imagine, right, a particle is presenting a smooth aging if the material groupoid is not transitive but Lie subgroupoid of the frame groupoid. So we have a very natural definition for a smooth aging in here. So okay, let me talk a little bit about the material distribution. So we will construct a distribution over this manifold. So as like any distribution for any point here, we will have a vector subspace of the tangent bundle of the same manifold. Here the notation is the power set of the tangent bundle. Okay, to construct this distribution, we will take a family of local vector fields satisfying 3 properties. The first one is to be tangent to the beta fibers, then we will impose to be left invariant, where here we have the composition of one jet, and then we will impose that these local vector fields are in the kernel of this map, and this map is the first derivative of the restriction of the mechanical response to this set. So we have here a family of local vector fields which is not empty because the zero vector field is inside this map. And then with this family we generate a distribution of this manifold which is called the X-material distribution. Then by using the groupoid structure, in particular the section of identities and the induced tangent of the source map, we can project this distribution into another distribution on R. So we have two distributions, and both distributions are differentiable and are integrable in the sense of Stefan Sassman. So we have our associated foliation, which are called X-material foliation and base X-material foliation respectively. So notice that this foliation is a foliation of R, while this foliation is a foliation of this manifold. Okay, we have distributions, our material distributions, we have our material foliation, and then here is our evolution equation. Okay, if we take this condition and we consider your vector fields in their local coordinates, if you impose these three conditions, what you have is exactly this evolution equation at X. So it is only the imposition of these three conditions over the local coordinate of the vector fields. So you have here an equation where here are the variables which depend on the time variable t. So we have our evolution equation at the particle x. So let me present just a couple of results just to show you the meaning of this, the meaning and the usefulness of these tools. So first, the material foliation. The base material foliation, you know, it was a foliation of R, and the meaning of this result is this one. What happened is we can divide the whole R into pieces in which over each of these pieces the evolution is exactly a smooth remodeling. So you can take whatever evolution you want, that I can ensure you that I will be able to divide the time into pieces which are a smooth remodeling. And the important part here is that this division is in fact a foliation which has important geometrical consequences, and it is maximal in the sense that there is no another foliation which is coarser and it satisfies this property. So this is a very intuitive result which can be proved by using this foliation. You can divide the time into little pieces of remodeling. So maybe there is a one interval where we have a remodeling, then some points of changing, then you have another remodeling, and something like that, you know. But this division is obtained by this foliation. That's what is important. Then by using the distribution we can prove this theorem in which we claim that smooth remodeling processes are characterized by this condition. The dimension of this leaf have to be equal to 1 for each t. So by using the evolution equation, what we have is that a material particle is presenting a smooth remodeling processes if we can find solutions for this equation with lambda non-zero. Right? If we're able just to find one solution, you have a smooth remodeling process. You have proof that your evolution is in fact a smooth remodeling process. On the other hand, for a smooth aging process, we have to prove that the dimensions of these fibers is constant and the dimension of this fiber is 0. So by using the evolution equation, what we have to prove is that this equation has a constant dimension and there are not solutions with a lambda different to 0. So if that happens, what we have is a smooth aging process. In another case, what we can do with this equation is to discover how is my evolution, where we can find in intervals of remodeling when there are intervals of changing or of aging, this kind of things, So, of course, there are much more information about this approach. There are much more results, but I just wanted to present you just some of them, just to, as I said, to convince you that this kind of tools could be useful to understand better what kind of evolution could we find in different kind of materials, So thank you for watching this video. If you need any other information, something like technical details, proof, maybe you want to talk about a generalization or an application in another field, or maybe you want some examples, then you can contact me, or you can read any of these references. The first one is a book. It's a book establishing the foundation of this new approach, and the other are papers talking about this the application of this approach in general. And for example, here we have generalization of this approach to the most general case which you can imagine, in which we are working with any subgroupoid of any Lie groupoid which you can imagine. So that's all, and thank you again, and bye bye.